everyone, my name is Sasa Stamenkovic and I'm a field application engineer with OneSpin solution. I have a pleasure today to speak with Sagheer Ahmad. Sagheer is an SoC architect and director of the architecture with Xilinx. So Sagheer, thanks a lot for spending time with me today.
Thanks, Sasa, my pleasure.
Nice. So my understanding is that Xilinx is today spending time and investing effort in automotive industry. Can you just tell me a little bit about it? So what do you do there? How is your development going?
Right, so we have been providing solutions for automotive areas, and in fact, before automotive, we have been providing solutions for defense and industrial and other segments where the safety and higher level reliability are required. For automotive, one significant difference is that safety is required for consumer products here. In general, safety requires both the verification of systematic and random faults.
Yeah, so there are these two types of the faults that you are now mentioning. So can you maybe tell me a little bit more details of what is the difference between them and how do you verify them nowadays in your flows?
So specifically for automotive, automotive safety standards such as the ISO 26262, which defines the ASIL standards, it clearly requires two types of errors to be handled. One is the systematic ones and the other ones are random ones. The systematic ones are the ones which are due to the process of development. So the standard
the development of the design itself?
The development of the design or the device.
I see.
So basically the standard requires and has stringent requirements specified for the development process to be such that you have the design verified against the specifications such that there are no errors in the development.
Okay, so that is at the end of the day really functional verification of the design.
That's essentially the finding bugs and making sure that the development is bug-free.
Our traditional verification process. And then on the other side, these random errors?
On the random error side, these are the errors which are due to environmental conditions, such as soft errors or any other single event upset errors or the random errors. The safety requires that the solution needs to have detection mechanism for random errors and provide solutions for handling them, some mitigations or some responses to them.
Okay, so these are something that are these errors are happening in the field at the end of the day. So
right,
something we cannot really predict upfront, but we need to, if I can say, safeguard
right.
them.
The way safety standards are that you take care of the the systematic ones as part of your development, but there are some which are going to be in runtime during the lifetime, and they have to be handled as part of the runtime or lifetime. So they are the random errors.
I see. Okay, so my passion is really formal verification. Do you think that there is any angle for formal verification which can be applied in your verification and the development flow? Because safety standard is quite rigorous. That's what I've heard, what I've been told.
So as we mentioned, that the systematic errors have to be verified against specs, and in fact, they have to be trackable. So the formal methods are more methods which are rules-based and certain in terms of their outcomes. So I think formal can play a significant role in terms of verifying against the intent or against the specifications. In fact, we are using formal for some of the things such as connectivity verification, some of the arithmetic unit verification, also the equivalence checking of the source against the synthesized logic.
And all those are formal based. So you get the exhaustive proof that if you run this connectivity that you're mentioning, you get a full proof that two nets in your designs or two pins or whatever we call them are connected properly and according to the spec, right?
Right. And again, the formal, in terms of rationalizing the tracking part, here's the spec and the intent is, the design is this. Formal can unambiguously prove that yes, that is the case.
Yeah, that's nicely said. I like that. Okay, nice. So, do you think that there is anything else that we from the EDA industry can provide you as solutions in terms of the tools to help you with this design and verification process?
Right. So one of the things we're looking for is the tools for the verification of safety mechanisms, where I believe formal can be very useful. The other is the diagnostic fault analysis or the random faults analysis. The traditional verification is focused on the systematic faults verification, but we have some gaps in terms of the tools to automate the random fault analysis.
I see. Okay, so really to shorten the process of the verification and not do stuff manually, which you may be doing today, but having the tool that verifies
Right.
both the hardware safety mechanism and at the end of the day the propagation of the faults, whether they are detected. So that's kind of the summary from what I got from you.
Right. I think as we discussed earlier, the safety requires all these to be such that they are trackable. We have to be able to rationalize the coverage is so and so. It has to be automated through some tools.
And the standard requires that, so with the
Right.
different levels that you mentioned. Great. Okay, Sagheer, thanks a lot for talking to me today, and everybody, thanks for joining this video. See you next time.
Sure.